Automatic Addison.
In this tutorial, we will explore the Nav2 Simple Commander API, a powerful tool that simplifies robot navigation programming in Python. We'll learn how to use this API to control a robot's movement, plan paths, and execute various navigation tasks without getting bogged down in complex ROS2 details. This guide will help you get started with the most important features of the Simple Commander API. By the end of this tutorial, you will be able to build this. You can use the Nav2 Simple Commander API in many real-world situations. Here are some examples. Home help. You can create robots that can clean your house or bring you things from other rooms. Warehouse work. You can build robots that check items on shelves or pick up and move things around the warehouse. Farming. You can develop vehicles that plant, check, or pick crops. Security. You can make robots that patrol areas or quickly go to places where there might be trouble. Healthcare. You can create robots that bring medicine to hospital rooms or clean areas to keep them safe. To get started with the Nav2 Simple Commander API, you'll need to set up your workspace. Follow these steps to create the necessary folders. Open a terminal window. We're going to cd ROS2 source Yaboom ROS master Yaboom ROS master navigation. Create a folder, makedir scripts, and create a folder for the makedir for the helper files you will create. So we're going to call it Yaboom ROS master navigation. And these are the Python-based helper files. And by convention, you create a directory of the same name as the package. So we do makedir Yaboom ROS master navigation. And let's cd into it. Change directories into it. And let's create our first file. So touch __ init __ .py. Okay, that's the first thing we need to be in there. Now we will create a goal pose message generator. This generator is important for our navigation task because in ROS2, robot positions and orientations are often presented using the posed stamped message type. And I'll show you what that is right now. Let's Google pose stamped message ROS2. That's this type right here. So this message type includes not just the position information, okay? It also includes the orientation information, but it's stamped as well with the header. Okay, so we'll click on the header, and the header has the timestamp, okay, and the frame ID, which are essential for accurate navigation. So let's go back to let's close that, go to the terminal window. So creating a function to generate those post-stamp messages will simplify our code when we need to specify goal positions and orientations for our robot. So let's clear. And let's create a new file. So I'm going to touch pose stamped msg generator.py. Make sure I spelled that correctly. Touch pose stamped message generator.py. Okay, and let's go over here to my repo. Downloads. Yaboom ROS master. You can pull all of this off of GitHub. Scripts. Nope, not scripts. Yaboom ROS master navigation. Highlight it and open with Gedit. Okay, here's the code. And let's go over here. Let's do Gedit pose stamped. Open it. Go to Gedit. Here's our empty file right here. And we need to Control A, Control C, and Control V. Copy all this stuff into our new pose stamped message generator code. Okay. So let's get it. Pose. So what does this code do? What does this code do? This script provides a ROS2 node class called the pose stamp generator that creates geometry messages, pose stamp messages. The class provides a create pose stamped method right there that takes the position coordinates, x, y, z, the orientation as a quaternion, qx, qy, qz, and qw, which is specific format for angles, and then the frame ID, the map frame. Alrighty, let's close, save and close. All right, and now I will show you how to create a script that will send a robot to a single goal location called a goal pose. So you can find a bare bones official example for sending a single goal on the GitHub. So let's go here, Google, on the GitHub for Nav2, GitHub navigation. What's the name of the file? I think it's called example nav2pose.py. Example nav2pose.py. See if we go straight to it. Yep, right here. So let's click the one for Jazzy. And you can see right here, we've got an example nav2pose file on the official GitHub for the Nav2 Simple Commander API. Here's the URL up top. And that's very bare bones. Okay. And this code is good, but it's missing some important functionality that you'll need for a real-world production mobile robot that needs to navigate in a dynamic environment with people moving around, objects of all shapes and sizes. And so for this reason, we're going to use this code as a basis and then add additional functionality to make it more useful for a real-world project. Okay, and our navigation script will assume the initial pose has already been set either via RViz, the command line, or some other method. And to create this script, we need to go back here and go into our scripts. And let's do touch nav2pose.py. And let's open it. And let's go over here to the code that we've written. Open with Gedit, Control A, Control C, and let's copy this in here. Save. And close. So make sure you save it and close it. And let's take a look at it. So what does this code do? This code sets up 3 ROS2 nodes. So we've got the go to goal pose node, which subscribes to goal poses and initiates navigation. It also publishes an ETA, or estimated time of arrival, on navigation status. It handles feedback as well, navigation feedback and result processing. Okay, you can find in here cost map clearing as well, right in there, to handle dynamic obstacles. Things like people that are moving across, you want to clear those off the cost maps pretty quickly. That's what this does. Now we've got the get stop navigation signal node, and that allows external navigation of navigation tasks. And we've got the get current velocity node, which monitors if the robot's moving forward, which is used for cost map clearing decisions. And down here below, you can see that the script uses a multi-threaded executor to run all nodes concurrently. It implements error handling and proper shutdown procedures. Key features include dynamic obstacle handling through cost map clearing. You got the, as I said, the real-time status, ETA updates, the ability to cancel navigation tasks, robust error handling, graceful shutdown. You need all of that for a very robust script, and that's what this script does. Very useful. This script right here is very useful for a production robot. All right, let's close that down. So in the same directory, let's create another script called test nav2pose.py, and this will be our test script. Let's get it test. And this is the way, when we're ready to test navigation, how we can send a goal pose from the command. So not from the command line, but from actual code. You can also send it from command line. I'll show you how to do that. So here is the command for that. We'll show you that a little later, though. Yeah. Okay. Here is the command right here to send from the command line. But we want to send everything from a script. right, so let's go and go over here. So here is our test nav2 pose. I'm going to open up here, open up with get it, Control A, Control C, and let's do Control V in here. Got a lot of different tabs open here with the code. Okay, so save it. So this script right here creates a ROS2 node that lets you send the robot to predefined table locations. You can see that on lines 52 through 56. So imagine we're in a cafe, we've got our cafe world, and we have different tables numbered right here with different X and Y coordinates. When you select a table number, the code generates and publishes a pose stamp message containing the X and Y coordinate for that particular table location, which tells the robot where to go. The program runs in a continuous loop, asking for your table selections until you quit by entering Q. Q is where you quit, down here on line 107. Or you can press Control C, allowing you to send the robot to multiple locations in sequence. Okay, so you're probably wondering, how did I determine those coordinates for our test file? Well, to do that, I did this. I'll show you here. Let's open up RViz. Okay, and I have a new terminal window. You're going to do ROS2 topic echo / clicked _ point. Enter. And at the top of RViz, we're going to click the publish point button. And here's our first table. We can see the leg here, and you just click somewhere near it. All right, just click it. And then over here, you can get the X, Y, and the Z coordinate. Z is 0, but the X and Y coordinate of a particular location that you click on the map. And you can just keep doing that for the different tables. So publish point, go to table 2. Publish point, go to table 3. And it'll just publish over here and update. So that's how I got the X and Y coordinates for our goal locations in the test script. Okay, now let's close everything. I'm going to Control C over here. And let's create an assisted teleoperation script. So this script will allow you to manually control the robot while automatically stopping it when obstacles are detected. And this feature also helps prevent collisions when you're manually sending velocity commands to steer the robot. You've got a bare bones example on the Nav2 GitHub, but we will go beyond that script to make it useful for a real world environment. So we need to create a Python script that implements this functionality. cd ROS2, cd source, cd yaboom, cd yaboom ROS master navigation, cd scripts, and let's create the script touch assisted _teleoperation.py. And let's do get it assisted teleoperation.py. Going to go over here, pull the code, same code that's on my GitHub. Go into the navigation folder, go to scripts, assisted teleoperation. Open with get it, Control A, Control C, Control V. We are a pro. Yes, I know you can just clone my entire GitHub repo to your workspace and do all of this automatically, but it's important you know how to build everything up from scratch brick by brick, because most likely in your professional career, you will not be using a Yaboom ROS Master X3. You'll have to adapt this to your own work. So the general steps are pretty much the same. So let's open it up. Okay, we have it here. And this script subscribes to the cmd-vel teleop topic to receive velocity command from the user. All right, and it manages the assisted teleoperation action across the Nav2 stack. Handles cancellation requests as well. All right, it also, like the Nav2 pose that we created, we periodically clear the cost map of any dynamic obstacles, temporary obstacles. Okay, and the Nav2 stack will receive these cmd-vel teleop commands, and it will publish the safe velocity commands to the cmdvel topic. Okay, so it's important to note that the cmdvel teleop is the input topic for user commands, while cmdvel is the output topic that sends commands using the cmdvel relay script we created in an earlier tutorial. Okay, that goes to the mechanism drive controller cmdvel topic, which then moves the robot. Okay, now let's close everything. And let's go over here to the CD Yaboom bring up. It's clear. Okay, and let's go into the launch. Let's open up ROS Master Navigation Launch. Let's go through here. What do we need to uncomment? What do we need to uncomment? Assisted teleop, let's uncomment that. We just added that node. Nav2 pose, uncomment that piece. Just added that. Okay, and then let's uncomment that stuff down below. So assisted teleop and Nav2 pose. Save. And close. Now to ensure our package has all the necessary dependencies, we've got to go here. CD Yaboom ROS Master Navigation. And let's edit the package.xml. And we've got everything in here. Built-in interfaces, geometry messages, navigation 2, Nav2 bring up, simple commander, slam toolbox, stood messages, TF2, everything is in there. These dependencies are required for the assisted teleoperation functionality to work properly with the Nav2 stack. So make sure that you have them in there. Save and close the file. Now let's clear. Now, to properly build and install all our Python scripts, including the new assisted teleoperation script, we need to update the CMakeLists.txt file. So do get it, CMake, and let's properly edit this. To make sure we've got all the necessary stuff in the CMakeList.txt. We just added some new stuff. So everything over here in the top with the dependencies is good. Okay, we've got our cmdvel relay. Let's see. Okay, so under this right here, we need to add this code. Underneath here. Okay, we're a mint Python install packages. So this block on line 37 and 38. Okay, make sure that we install the Python modules. Make sure you have that code. And then below that, let's add this piece, installing the Python executables. Down here, assisted teleoperation, Nav2 pose, and test Nav2 pose. Okay, and when you're done with that, save and close. Now we need to build the package. I'm going to open up a new terminal window, and I'm going to go cd ROS2, and let's do ROS dep install -- from paths src -- ignore -src -y -r, and press enter. All required ROS dependencies have been installed. Now run a colcon build, and source ~/.bash rc. So colcon build and 2 ampersands source ~/.bash rc, and press enter. Everything's built. Good. Okay, now I want you to launch navigation. I have my nav short script. Okay, and let everything come up cleanly. Good, good, good. Just set a good pose. Click pose estimate. Set this and drag. Nice, good pose. Okay, and let's open up a terminal window. 2 terminal windows. Okay, and in one, I want you to do ROS2 topic echo / goal underscore pose. Sorry, / goal underscore pose / ETA. Type enter. And then over here, we're going to do ROS2 topic echo / goal underscore pose / status. Okay, like that, and press enter. And then in another terminal window, I want you to publish a goal pose. So we're going to do it like this. ROS2 topic pub, goal pose, goal, geometry messages, pose stamped. Then we've got the header timestamp, the map frame ID, and the position and orientation. Let's have a look. The robot, okay, all good. And when we press enter, the robot should start moving. It is moving to the goal. So you see the robot moving to the x = 2, y = 2 position. Pretty cool. All right. Alternatively, let's just press Control-C. Stop that. So robot reached the goal. So alternatively, you can send the robot to different tables in the cafe world using your test script. So clear ROS2 run, yaboom ROS master, navigation, test nav to pose.py, -- ROS -args -p, and then use sim _time. Okay, and then assignment true. So we use simulation time. So ROS2 run, yaboom ROS master navigation, test nav to pose, ROS args, and then pass use sim time, and then assign true. So depending on your CPU, you might have to send commands more than once. I sometimes have some issues. Doesn't work the first time, but this is how you can send the robot to different tables. So press enter, and here we go. Available tables, we got table 1, 2, 3, 4, and 5. Okay, how about we send it to table 3? So I'm going to do 3, and then press enter. And let's see if it's going. Yep, you can see the robot going to table 1, 2, 3. This table down here I called table 3. And if you go to Gazebo and zoom out, baby, come on, come on, come on. See our robot moving down there? It's moving away. Zoom out more. Okay, you can see at the bottom of the screen. Right there, tiny. Computer's moving slow, but you see it in RViz, which moves a little quicker. And you can see it move to table 3. Pretty cool. And you can see in here the status. We had in progress, and progress succeeded, the status of the goal. And over here, we have our data, okay, which we had way up top here, the ETA data, expected time of arrival in seconds, 385 seconds and so forth, all the way down here, our time. By the way, if you ever want to stop an ongoing, cancel an ongoing goal, you would do ROS2 topic pub, and then do stop, navigation, go to goal pose, and then do stood _ messages /msg /bool, and then data :space true. You're going to publish true on the stop, navigation, go to goal pose topic if you ever want to do a goal. So cancel an ongoing goal. So sending it to table 1, way over here, I want to cancel. Okay, we're canceling. And you can see we have a canceled message over here in RViz where we canceled the goal. Control C. All right. Let's quit that. Let's quit everything. Quit, quit, quit. Okay, now I want you to start navigation again. We're going to do assisted teleoperation. Let everything come up. Okay, and let's set the pose. And to do assisted teleoperation, let's clear. Let's do ROS2 topic info cmd val teleop. Okay, and it's a twist message, and we've got some subscribers on there. So if you want to teleoperate the node with obstacle avoidance capabilities, you will publish to the cmd val teleop topic a twist message. Teleop. So like that. Okay, here's the command. We're publishing at 10 hertz. So pause the video if you need to. Okay. And press enter. Okay, let's go over here. And you can see the robot moving around using assisted teleop. Okay. And if you were to move this robot towards an obstacle, you can see this happen now. Let's make this 0. Let's move it directly towards an obstacle. Move it towards this wall. I'm going to come into the frame in a second. Cool thing is it will use obstacle avoidance with assisted teleop. It's one of the benefits of using it. You want to bump into things. So you see, it's not running into this area right here. This looks like a file cabinet. Even though we're continuing to publish the velocity command to make it go straight with 0.2 meters per second, it refuses to run into that obstacle right there. So you can see it in action. And to cancel assisted teleop, you can open a new terminal window. Okay, open a new terminal window and do this command. To cancel, ROS2 topic pub, cancel assisted teleop, stood messages bool, data true, and once. Here's the command. And you just publish, and it'll cancel assisted teleop. No more teleoperation going on. So to restart everything, let's just control that. Let's cancel. To restart everything, you would just publish again to the cmd val teleop. Okay, you just start moving it again. Okay, you just start like that and start publishing again. Assisted teleop. Let's actually make it go backwards. Minus 0.2. See if this works. Yeah, starting to move back. And that's it. Control C. Cancel. Okay. See, canceling assisted teleop and canceling. So we've gone through a lot. In this tutorial, we have explored the Nav2 Simple Commander API, and we've implemented various navigation functionalities for our robot, including basic goal navigation, predefined locations, assisted teleoperation. You can find lots of other examples on the Nav2 GitHub, and these implementations demonstrate the versatility of Nav2, combining autonomous navigation with user input for flexible control in various scenarios. So the skills you've gained in this tutorial give you a really strong foundation for developing more complex robotic systems, which are applicable to real-world robots with minimal modifications of the code. That's it for this tutorial. Thank you for watching and keep building.